Okay, before I start on today's notes, why don't we do a quick little bit of review of what we already have covered in this unit?
Jennifer Patalio, can you please come to the office? Jennifer Patalio, please come to the office.
So it's been a while since we've done some of this stuff. Let's do a quick little bit of review of what we have talked about. Probably the first thing that we talked about is just some basic properties of gases. And there are three main things that, I guess when we talk about matter, that they have the ability for motion. This was like the first thing we started with. Solids have vibrational motion. You guys remember that term? Whereas then liquids, yes, they can vibrate as well. Like, not that it doesn't have that ability, but it also has what we call rotational motion. Rotational. That's rotational. Does that sound familiar? And then the last one, gases, which we're really going to focus on, they also have the ability to translate. So what do I mean by that? Well, if we were to imagine particles, I mean, gases are still particles. Can we see them? Well, no. But, I mean, I often joke about this here. I'm going to hit gas towards you guys. And I am hitting particles towards you. When you feel wind, you're feeling those particles hit you with enough energy and enough of them that you actually get blown backwards, right? It's not some sort of magical substance. There are particles in the air there. Well, actually, the particles are the air. Someone mind grabbing that door? So gases have the ability to move around. This is basically the key thing we want to talk about here. Now, let's say these gases are inside an enclosed container, though. So let's say that we're not talking about just gases going anywhere, but let's say we have a balloon or something like that. Okay. These gases are going to then move around, and they're going to hit the sides of the container. Well, hitting the sides of the container could be considered like a push. Does that make sense? And a push is a good example of a force. And so one of the things we might want to talk about is force over area squared. Area squared would be like a cross section of like a two-dimensional type area, right? And if you have force over area squared, that's actually equal to your pressure. Okay. One of the things that we started talking about is the idea that pressure in different places on Earth will differ. For example, at sea level, what's the pressure typically supposed to be? 101.325. Roughly 100 though, yes. Okay. But those aren't the only units we have. So 101.325 kPa is one unit of pressure. There's another unit of pressure, millimeters of mercury. And this unit was based on a guy named Torricelli. He made the first instrument that measures pressure. You guys remember what it's called when you have an instrument that measures pressure? Yeah, good. It's called the barometer. Yeah. And there is one more unit. It is called an atmosphere. And it's probably maybe I'd say the least common of the ones you'll see otherwise. But we've defined it as exactly one atmosphere as at sea level. And so one of the first things we talked about then was, can you convert between these three units? So far, so good? Okay. The second day, we talked about something called Boyle or Charles laws. And basically it has to do with manipulating either pressure or volume or temperature. And eventually we just kind of put them into what's called the combined gas law. So let me write them out one at a time here. P1V1 equals P2V2. That was Boyle's law. Boyle's law. Basically it says that the pressure and the volume have a opposite relationship to each other. As one goes up, the other goes down. If I were to draw a graph of pressure versus volume, which you should have done in your lab, by the way, the graph should hopefully look like this. And someone said this word, I heard it there, it's a reciprocal. This is one of the reasons I love teaching math and science, is that they're so intertwined. Because this reciprocal relationship we're doing in chemistry, I'm pretty sure I taught all of you guys this for the most part in math as well. The idea of how as one goes over, the other one comes down. Another law we learned would have been volume over temperature equals volume over temperature. And that one was Charles' law. And hopefully what we'll discover here is that our graph looks like this. You guys remember what we call this sort of graph and relationship? Direct is a good word, yeah. Linear is also a good word to use. I'd accept either of those, direct or linear. Morning. I've drawn this graph like this on purpose because Charles managed to figure something out. He figured that if you manage to make this graph go backwards, say this is 0 degrees Celsius, if you can go backwards, he figured out where this graph would have ended up at. And it was negative 273.15 Kelvin, which we have a name for. Good, we call it absolute zero. So hopefully when you guys did your lab, you have graphs that look like these two graphs here. Ultimately, sorry, go ahead. Yeah, 0.15. I usually let you guys skip the 0.15. 273 is usually good enough. Ultimately, we can put all of this then together in what's called the combined gas law, which looks like this. And that's more or less where we finished before the break, was with a lot of math formula type stuff. There actually was one more lesson than that, though. There was one talking about what's called an ideal gas. So let's probably talk about that one too. It was a little bit more of a theory type thing. Ideally, gases will always move randomly. They'll always bounce off of each other. But there are two conditions in which gases do not behave ideally. And those two conditions are high pressure and low temperature. I just want to kind of envision those a little bit. Let's say that you had, again, a box here, and you've got all these molecules inside. But this is really not that much pressure. When these guys hit the sides of the container, it's not going to be that much pressure at this point here. But let's say that we really pack this thing full of molecules. I mean, really pack this box full. So it's a highly pressurized gas. Well, now can it really behave as a gas anymore? I'd say, well, no, it doesn't really have the ability to behave as a gas, because can these particles even move? Well, where are they going to move to? There's no room for them to move. Right? And you might suggest that it won't even act like a gas. It would act maybe more like a liquid or a solid, because these particles are so close to each other. I like to use analogies. One of the analogies I'd give is like, here we have students in the classroom. Imagine you're all gas particles. Do you have the ability to act as gas and stretch and move around? I'd say, sure, you do. Now let's shove like 500 kids in this classroom. We might be able to fit us all in here like a clown car, but will you be able to move around and stretch and translate like you'd like to do? I mean, you might be able to wiggle a little bit, so maybe you have a little bit of vibrational motion. Maybe you could like slightly maneuver past somebody else with some rotational motion, but could you walk wherever you wanted to if there were 500 kids in this room? No. So therefore, ideally, you'd be able to do this, but that's one condition, high pressure. The other one is low temperature. Low temperature probably makes sense on its own as well. Temperature is really a measure of all of these molecules, how fast they're moving. And if this molecule here is really moving very slowly, it's not really going to bump off the sides of the container all that much. Maybe if this molecule right here hits this molecule, rather than bouncing off each other, they might start clumping together. And rather than being separate, they might actually start to become a liquid instead. So, I mean, if we could get things to really low temperatures, gases would act kind of weird as well. But otherwise, we would consider a ideal gas to be able to always act like a gas, and a real gas would be under these two conditions. That make sense?
Wait, real?
So, like, an ideal gas would be under, like, normal conditions. Does that make sense? So, like, right now, there's gas in this room. Is it acting as an ideal gas or a real gas? I would say it's acting as an ideal gas. It's moving around. It's doing what normal gas should do. But let's say that there was a whole bunch of gas pressurized inside, like, one of those CO2 canisters that you might use for, I don't know, whatever you use them for. We use them for, like, whipped cream. You guys ever used those before, where you like put them inside like the little container thing, you turn it upside down, you can buy those canisters. So, oh, that'd be kind of scary. Compressed gases are kind of dangerous sometimes. So, I used to use CO2 canisters in my hockey skates. Any of you guys play hockey? You ever see those pump up skates where you used to like? There used to be a thing on the tongue of the skate where you could like pump up your skates. You ever had those? They were really popular probably 15 years ago. I don't know that they are anymore. Used to use CO2 canisters. Anyways, I'm getting off topic here. My point was that if you had a highly pressurized gas, maybe those molecules inside, they really can't ping around all that much because there's no room for them to, right? So then you'd call that a real gas as opposed to an ideal gas. So far, so good? Okay, so let's move on. So topic 5 out of 6. So, before I start reading off my notes, just want to give you guys an example from everyday life maybe before we start. The air we breathe, is it all one substance? No. So, I mean, if I were to, again, like let's say this is a box and there's air inside, you could have some nitrogen gas molecules, so I'll draw them like this, N2 everywhere. But we don't actually breathe in the nitrogen so much. What else is in the air we breathe? Oxygen. There's less oxygen than nitrogen. Here's the point I want to make. As I'm drawing this, did I draw them like all the oxygens on one side of the room and all the nitrogens on the other side? No. I drew them kind of spread out. Right? What is in this space right here? Literally nothing. Right? I mean, we could almost consider it to be like a vacuum, I guess, a really small set of vacuum, not a vacuum cleaner, right? But like a vacuum means like there is volume, but there is no matter there, right? We could even throw some CO2s here and there. Okay. So let me go back to my first topic here. Let's say we want to try combining these things. Let's say we want to combine gases. Gases have the ability to mix. Does that make sense? They're always going to mix nice and evenly. The term we would use there would be homogeneous or homogeneous, however you want to pronounce that. Okay. So let me read off my slides here then. In the early 1800s, scientists began to realize that when you started mixing gases, they always seemed to do so in, here's the really key thing here, whole number ratios. I'm going to show you what this means in a second. But I'm going to highlight this term here, whole number ratios. You guys remember the name Avogadro? Heard his name before? He was famous for Avogadro's number, which was like 6.02 times 10 to the 23 molecules in a mole. That's not relevant, but that's what he was also famous for. He had a hypothesis. He said that equal volumes of gas at the same pressure and temperature must have the same number of molecules. Here's what that means. So I can draw this. Let's say that here you have a pressure of, let's just say 1 atmosphere. And you also have a volume of 1 liter. And let's say inside here you have hydrogen gas. What Avogadro suggested is that, let's say you had the exact same type of pressure, so you still have 1 atmosphere, and you still have 1 liter. Said, well, let's say it wasn't hydrogen. Let's say it was oxygen gas. Doesn't really matter. He said there would be equal number of molecules. Here, I've drawn 4 molecules. Right? 1, 2, 3, 4. Well, basically, he suggested that there should be the same number of molecules here if it's a different type of gas. He suggested it doesn't matter what kind of gas it is, if it has the same pressure and has the same volume, it shouldn't matter whether it's hydrogen or oxygen. And maybe that makes some logical sense when you break it down to like a microscopic level, because hydrogen is just this little bitty particle right here. Right? Now, oxygen, still pretty small. It's a little bit bigger, so why don't I draw it that big? Does it really matter that it's oxygen versus hydrogen in terms of like size here? I mean, really, all of this dead space right here, does it really make a difference how big this molecule is right here? Does that make sense, what I'm getting at? That was his idea, is that equal volumes at the same pressure and temperature, I didn't mention temperature, should have the same number of molecules. Now, rather than counting things as molecules, though, we have a better way of counting them. We count them as moles. So rather than saying you might have 4 molecules, you might say, well, if you have 4 moles here, you might have 4 moles here. So I have some numbers for you to write down. No, we'll get to that in a second here. Let's do this example first. let's say that we're going to combust C4H10. Anybody know what C4H10 is, by the way? Close. Nope. Taking stabs in the dark. This is butane, which is what we're going to use in one of our labs. We're going to use a butane lighter to try to get some gas. So let's say we want to combust butane. What does combusting butane mean? Burning it. So what do you burn it with? Oxygen. What are you going to make? What do you always make when you combust things? CO2? Water. Is this something else? Okay, one more thing I need to do before I start, and then I'm going to relate it back to something that I said I'd come back to. We need to balance this thing. So, how do I balance it? Well, let's see. I'm going to need 4 CO2s, because that'll make the carbons balance. Hydrogens, I'm going to need 5, because that'll give you 10. Problem I'm going to come across here is now for oxygen, there's 8 oxygen right here. And there's 5 more oxygen right here, which means you have a grand total of 13. But you can't turn this guy into 13. You guys remember how to do this? Double it, yeah. So make this guy 13 now. And then double everybody else. So this should now be 2. This guy is now 8. And this guy's 10. Let's see whether this makes sense now. 8 carbon to 8 carbon, and that's a bit of a mess there. 20 hydrogen, and that's 20 hydrogen. This is now 26 oxygen. And then here you'll have 16. And 10 more, so that'll be 26. Does that make sense so far? Yep. Okay, now let me go back to something I mentioned earlier. Scientists begin realizing that they always did so in whole number ratios. These are those whole number ratios. It's like a recipe. You need 2 molecules of butane and 13 molecules of oxygen in order to make 8 molecules of carbon dioxide and 10 molecules of H2O. This may seem kind of weird, but on this side over here, you have 15 molecules total. On this side over here, how many molecules do you have now? 18. We managed to create more molecules. That's okay though. It just means that the molecules are of different sizes. Here's what they figured out then. Let's say you had 2 liters of this stuff, and you added it to 13 liters of this stuff. It means you would make 8 liters of this stuff, and 10 liters of this stuff. Essentially, I could start with 15 liters of gas, and turn it into 18 liters of gas. Does that make sense at all?
I don't understand.
That's
I don't understand how you figure out the mole.
okay. So well, let me skip that and come back to this idea here. If we were to break this down as like a recipe, if you had 2 molecules of this stuff and you had 13 molecules of this stuff, you'd have enough stuff to fulfill your recipe. Does that make sense? And if I drew them out, it would look like here's a C4. I'll draw it like this. That's a C4H10. So I need 2 of them. And then we need some oxygen. So I need 13 of these
Hannah
guys.
Poffenroth, can you please come to the office?
9,
Hannah,
10,
please come to
11,
the office.
13. So if you start with all of this stuff, it's going to make, what did I say, CO2 and water? So it's going to make 8 of these ones. 1, 2, 3, 4, 5, 6, 7, 8. And 10 of these guys. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There is not a law of conservation of molecules. You can start with 2 of these and 13 of these, which is 50 in total. And when you're done, you can end up with 8 and 10, which is a total of 18. You can start with 15 molecules and end up with 18 other ones. Let me give you a different example here. Maybe this will help relate it. Let's say we started with AB and it broke down into A plus B. What kind of reaction is this? Decomposition. Okay, but let me change the reaction type. Let's say it was CaCl2. What's that going to break up into? Well, break up into maybe, let's say, Ca2 plus and Cl negative. But there might be two of these guys. This is what we did in the last unit. Here you have one molecule, and now you have three. I gave an analogy of my daughter playing with her Barbie doll or something like that, right? Lego pieces. There was one item, and we've now broken it into a bunch of different items. Does that make sense? Well, that same idea applies to gases here. You have two of these molecules. They're fairly large molecules. And you have 10 of these or 13 of these molecules. So originally you have 15 molecules when you start. When you're done, though, you actually have 18 molecules. Because when they've rearranged themselves, apparently it ended up making a few more. These are really big, these are really small, and these guys are, I guess, kind of in between. Does that make sense? Well, based on that, we actually have a recipe then based on liters. If we have 2 liters and 13 liters, it's going to give us 8 and 10. So let's try the example I had here now. Let's say that you have 120 milliliters of C4H10. How much oxygen do you need? So we need to figure out the ratio. This is 2, and that's 13. How much, are we going to need more oxygen or less oxygen? How much more oxygen? Well, 6.5 times. How did I get 6.5? 13 divided by 2? That makes sense. Because you started with 2 and you ended up at 13. Let me show you a trick I used to help keep track of this. There are 13 oxygens for every 2 butanes. You see how using unit conversions, those cancel? What units am I left with now? Oxygens. So you need a calculator here. What's 120 times 13 over 2? Okay, so think of it as a recipe. If you start with 120 milliliters of this stuff, and you use 780 milliliters of this stuff, how much total gas are we starting with then? $120 plus 780? 900 liters? Milliliters. Maybe here's a follow-up question. Let's figure out how much of these gases I should expect. So let me try a different one here. Erase some of this mess I have on here. What if I didn't want to figure out how much oxygen I needed? What if I wanted to figure out how much carbon dioxide to expect? So start with 120 milliliters of C4H10. But let's change it up here. Rather than making oxygen, let's try to figure out how much carbon dioxide we'd get. So put CO2 up here and C4H10 down here. What's the whole number relationship between CO2 and C4H10? 8 of these for every 2 of these. What am I really timesing by? 4. Why 4?
Because 8 divided by 2 is 4.
Because 8 divided by 2 is 4, right? If you start with 2, you're going to end up with 8. Right? So to go from 2 to 8, you need to times by 4. That's essentially what this is doing here. Because you see how those are going to cancel each other? So 120 times by 4 would be 480 milliliters of CO2. One more question then. Well, I solved for my CO2, so let me write this in a different color because it's getting a bit messy here. So this is 120 milliliters. This is 780 milliliters. This I just said would be 480 milliliters. Could we figure out how much water vapor to expect? How do you get from 2 to 10? Times by 5. Or if you really want to show the work, 120 milliliters of butane. There are 10 waters made for every 2 butanes being used. 10 over 2 is 5 times as much. So 120 times 5. Cool. So then this is 600 milliliters. How much total volume did we start with then? Well, this was 900 milliliters to start. How much did we finish with though? 480 and 600? $1080. More. Okay, let's talk about an engine of a car, for example. What happens in an engine of a car? It combusts. There's an explosion. Okay, and the explosion should ideally make the piston go up, and then momentum will hopefully make it come back down again. And then there's another explosion. It goes up and it comes back down. Why does the piston go up in the first place? This. We've exploded some materials that used to take up 900 milliliters. And after it's done, it now needs to take up 1080 milliliters. So what happens in the piston? Well, the piston then needs to expand so that those gases can expand is the best word. What were you going to say there?
It's the other way around.
What was that?
Like, basically gets
Like,
forced down,
by the explosion, and then it gets.
and then the shaft goes around and goes back up.
No, the explosion should cause the piston to...
Goes down. It goes over the top.
Oh, okay. Yeah, because it's other side of the piston, though, we're saying here, right? Because, you can always consider a piston as having 2 sides here. Maybe we're splitting hairs over not the relevant concept here. Because here you have, a basic piston like this here, and then it's attached to a shaft that's going to go up and down. And so you're talking about...
Oh, yeah, okay, yeah.
Right? Because what's going to happen is the gas is going to be inside one container, and it's going to force the piston up. But is up really down from the other perspective? Are we talking about the same thing, just backwards? We'll talk later. I think we're splitting hairs. The concept I want to make here, because I think I'm getting away from my point here, is that when you have a certain amount of volume, you can actually change that volume by undergoing a chemical reaction. And that's what this law here was, is that they mix in whole number ratios. And so the gas is going to you can end up having more gas when you're done. That gas would then need more volume, expand, and cause the piston to move up and down.
So, okay. That's the final answer.
Well, to this question here, I asked how much oxygen was needed.
So just the...
So the oxygen was the 780.
Okay.
Okay. But let's say I didn't ask about oxygen. Let's say I asked about CO2. Then it would be 480. Or if I asked about water, then it would be 600. What I could do then is ask you how much extra volume did you end up with when you were done. So you started with 900 milliliters total, but by the time you were done, you actually needed 1080 milliliters. So you're going to need more room now, because that volume is going to take up more space. Does that make sense? Okay. Keep going here. Avogadro then had a theory, basically. He figured that if all gases then have equal numbers of molecules and temperatures, we should be able to figure out a mole of gas, how much volume it takes up. And so you need to write some of these numbers down because they come up quite a bit. And I have them on the next slide here. At STP, you guys remember that term STP? So 0 Celsius, 101.325 kPa. It takes up 22.4 liters. 22.4 liters. But if it's at SATP, it actually takes up 24.8 liters. I'll show you some questions that involve this in a bit. So, STP means that 1 mole is 22.4 liters, and SATP means that 1 mole is 24.8 liters. Does it matter what type of gas it is? No. Because ultimately, there's lots of dead space in between all these gas molecules. it doesn't really matter whether it's oxygen or hydrogen or helium. They're always going to combine in these whole number ratios anyways. So, let me try another example here. Let's say we're talking about helium, which we use at, you guys ever used helium balloons before? They rise, makes your voice sound really squeaky. Okay. Here's my question. Let's say you have 3.5 grams of helium. How much volume should it take up? Let me show you how to solve a question like this. Start with grams. We don't typically want to work with grams in chemistry. Do you guys remember what we sometimes convert to for other units? Not from grams.
Oh, go there.
What's a better way of counting particles in chemistry, not in terms of mass? Moles. Yeah, let's convert it to moles. How do I figure out the grams to mole ratio, though? Where am I going to find that number? There's no other numbers up here to work with. Okay, so which one am I looking for? Helium. Okay, so what's helium's molar mass? I think it's 4.00. Where does that number go, with the moles or the grams? Is it 4 grams in 1 mole?
Grams per mole.
Or is it 4 moles in 1 gram? Which one of these two is it?
Grams per mole.
It's grams per mole. Okay, so then we need to put the 4 grams on the bottom here. Now, that's a good start. That gets us into moles, but now how do I convert to liters? Well, that's what I just wrote down here, is that at STP, 1 mole is 22.4 liters. So then I could say, well, here's a liter over mole ratio. See how those can cancel? In 1 mole, there's 22, wait, hang on, SATP. Which one's SATP? I screwed up. It's the 24.81. So, see if this makes sense. Your grams will not cancel because you divide by molar mass to get us moles. But any gas, regardless of what type, always takes up the same amount of space based on moles. So this mole right here will cancel with this mole here, leaving us with liters. So you have to take 3.5, divide by 4, and then times by 24.8. So I would expect 3.5 grams of helium should need about 21.7 liters. Does that make sense? Okay. Let's try another one here. Let's figure out the mass of methane gas that would be combusted at SATP if it produces 25 liters of CO2. So this question needs you to put together a lot of different skills we've just talked about now. First thing here is we're combusting. We need to write an equation. What's methane? Anybody remember? CH4. Good, okay. So CH4, what does combustion involve? Oxygen. Making CO2 and H2O. So this is like a recipe, it's an equation. Is it balanced? Okay, so that should be our next step. Let's balance this equation. Carbon's balanced, that's good. Put a 2 here for hydrogen, that balances that. And a 2 there, there we go. We're good to go. Okay, next question here. Here's the only number I was given, 25 liters of CO2. Means you made 25 liters of CO2. But is that what my question is asking me about? Is it asking me about the CO2? It wants massive methane gas. So one way of putting it is that it's almost like there's 25 liters of CO2. And the first thing I've got to do is figure out, well, how much methane volume would there be? Well, if this right here is a 1, and this one right here is a 1, do I actually have to do anything? No. That's good. But let's say this was like, say, a 4 right here. what would I have to do? Times by 4. Maybe a way of showing this, though, would be to say that there is 1 CH4 in every 1 CO2. See how that kind of cancels there? That being said, timesing by 1 is not all that purposeful. But in theory, we could have had to. Well, next step, I want to get to mass. What are the units I'm working with right now? Well, they're liters. How can I get rid of liters? What could I convert liters into instead that we've just talked about? Moles, yeah. Why don't I put liters on the bottom and moles on the top? That'll cancel out my liters. Here's my question, though. What sort of, where does a number go here? Well, it's SATP. So that's 24.8. Does the 24.8 go with the liters number or with the moles number? Okay. So that means it needs to go right here. So see if this makes sense so far. I've taken my CO2 and I've canceled it out and made it CH4. Which was kind of pointless because, to be honest, if I have 25 liters of CO2, I was going to have 25 liters of this stuff right here. By the way, how much oxygen would we need? Good. It would be 50. Because it would be twice as much. Right? And how much of this would I need? Also 50. Not that that was part of the question, but I could have solved for that. Because this is twice and this is twice. Does that make sense? Okay, last thought. We've now canceled our liters. We've canceled our CO2s. We now have moles left. What am I looking for, though? Grams. So let's put grams and moles right here and here. How am I going to find a number that gives me a grams per mole? The chart there, yeah, it's a molar mass. But molar mass of what? Of CH4, yeah. We're now talking about methane, so I need to take CH4 and find its molar mass. So carbon is 1201, and hydrogen times 4 is 101, but times 4. So where does that number go then? With the grams number. So we actually have a bunch of things to do with our unit canceling here. It's kind of like our first unit again now. First I had to cancel the CO2s, which I didn't really need to do because it was a 1 over 1 anyway, so that's kind of pointless. I had to cancel my liters using this new number I just showed you here. And I had to cancel this moles using a molar mass number. So let's put it all together now. 25 times 1 divided by 1 is kind of pointless. Divided by 24.8 times by 16.05. I got a final answer of 16.1794, etc. grams. How do I round it? How many sig digs do I get? This guy right here gives me 2. So we're going to need 16 grams of methane to make this work.
I got 16.6.
So 25 divided by 24.8 times by 16.05.
That shouldn't matter. Times by 16. It's 16.05.
Oh, wait a minute, that's why.
So what was the penalty?
16 grams basically when we round it. Okay. Kind of a hard topic to get back into, I guess. Let me recap, because that's it for my notes, right? Is that my last slide? Let me recap the skills I'm hoping to have shown you today. One of the skills I wanted to show you, probably the hardest to wrap your head around, is the idea, I had some pictures drawn here, that if this right here is 120 milliliters, and this is 900 milliliters, you don't have the same amount of volume on the other side. There's no law of conservation of volume. Volume can change. That's not a problem. They can take up more space. Okay. But what we can do is use that to help convert. So I really like showing it like this because then you can cancel your units and really you're timesing by a ratio. Like here you're timesing by 6.5. Here you're timesing by 4. Let me just make up a different example here. Just want to make sure you guys have this before we go. Let's say you had 4 A's and 7 B's and it made you 8 C's and 3 D. Hypothetically, let's say we started with 100 milliliters of A. How many milliliters of B would you need then? So maybe I'd say do something like this. Well, you have 100 milliliters of A. What's the relationship between A and B? Yeah, I mean, it's not quite doubled, but it's pretty close to being doubled. So I'm going to expect it to be just under 200. So to show this, maybe say, well, there's 7B for every 4A. You guys see how those would cancel there? So then 100 times by 7 over 4 means that you'd need 175 milliliters of B. So that's 100. That's 175. Could we then find C and D? Sure, you do the exact same thing. You'd times by, well, actually this next one's easy, 4 to 8. You're doubling basically, right? So that one's 200. That one's pretty easy. I mean, now if it's going from 4 to 3, it's going to be just under 100, right? So if I had to show that, it would be like, say, 100 milliliters of A. There are 3 D's for every 4 A's. So 3/4 of 100 is 75. Does that make sense? That's one of the skills I need you to have, is that the volume of each of these things here, we can actually find it in whole number ratios, which is why I highlighted this on the very first slide here. They realized that everything was a whole number ratio. Whole number, this is a whole number, that's a whole number. Is it in a ratio? Well, what's a ratio? A fraction, basically. You're dividing things. So that's one of the skills I need you to have. The second skill is, given that information, could you convert using these things here and convert liters into moles? Because if you can get liters into moles, you can get moles into grams. And that's what these last examples were about, is now that you have grams, you could cancel grams to get moles, and then use this ratio here to get liters. Or, backwards, you could actually use this liters number here and get into grams. That makes sense.
Can you show the ABC of D?
The one I was working on there again? Where was I writing that one now? Is it way down here? I don't know where I was writing it anymore. Here it was. Here, let me do one more example here then. Let's say that we had 75 milliliters here. You could then say take 75 milliliters, make it into liters, and then you could say convert that into moles using this ratio here. We're missing a number though. It's either going to be 22.4 or 24.8, depending on whether it's at STP or at SATP. So why don't we just use STP's number here? So we put 22.4 right here. You see how that could cancel my liters number then? Usually we want to then get into grams. We would just need to know the molar mass. Here's the only problem though. I made up random letters here. So I mean, if you knew the molar mass, you could try to find grams by doing one more step. Some of the questions on your, there's one question on your assignment for sure that involves these skills here. So I guess the key I want to point out is if you ever see SATP or STP, whoops, that's 22.4. There's actually a couple of values that are implied that can help you convert liters into moles. Okay. Any questions? So it's kind of a tough lesson for our first one back from our Easter week off. I have to really jump right back into chemistry mind again. Questions? Okay. Here are some different ideas for things to work on. There's a couple of chapters in your textbook you can take a look at. There's also some practice. There was a practice worksheet on my website. You also have your assignment to work on. Why don't you guys take a 5-minute break? When you come back, you'll have about half hour left. Work on something productive, okay? Get back into the swing of doing chemistry.
So if I get
One second. This one.
Did you? Oh, good.